Hello students, welcome to online 12th class. Let us start with physics section. See, the content of physics has 16 topics from section 1st and section 2nd, out of which we are going to study about the section 1st, which has 6 topics. Which are these? See, the first one is rotational dynamics. See, this chapter includes actually two topics. One is circular motion and another one is rotational motion, about which now we are going to study. The second one is mechanical properties of fluids. All these topics whose base we have studied in our previous standards. So in detail we are going to study about the same concepts. So third one from this is kinetic theory of gases and radiation. Then the next one is a new and important topic. From last 2 years it was introduced in detail. It is thermodynamics. The fifth one is oscillation. This is also a type of motion. And the last one from the section first, it is nothing but we are going to study about this is superposition of wave. We have studied about the sound wave, then in detail regarding wave we will discuss in this topic. So from these 6 topics from the section first, properties of matter, right from today we are going to start to study about the rotational dynamics. See, motion and different types of motion we have studied about. One-dimensional motion, two-dimensional motion, three-dimensional motion, that is translatory motion. In 2 dimension we have studied about the circular motion as well as the projectile motion, right? So some of the brief description about circular motion we have studied in our 11th standard. Now some of certain related aspects with circular motion we will study first of all in this rotational dynamics, and in detail study about the rotational motion, that is nothing but the rotational dynamics. So to study the circular motion first, or certain new aspects regarding circular motion, we must review or take a review of the previous articles which we have studied in our 11th standard, right, about the circular motion. That will help you in understanding the further concepts. So circular motion. What is mean by circular motion? All these things you are now familiar with. We are going to take a review about all these things. So it is nothing but motion of an object along the circumference of circle. We come across this circular motion in our day-to-day life also. That is the motion of hands of clock. Fine. Or say a different type of circular motion, that is planetary motions. Earth revolves around the sun, or different planets they are revolving around the sun. Then further moon is revolving around the earth. Likewise these are the planetary revolutionary motion. Or say the rotation of blades of fan about an axis, right? So now these different types, these are nothing but the different types of circular motion where the particle is performing motion along the circumference of a circle. Fine. Then as during the rotation or revolution, see what is the difference between these two? whenever we say the word revolution, it means the object is revolving around certain another object. Fine. The particles, each and every particle is revolving around certain another object, whereas when we use the word rotation, it means that the object is revolving along a fixed axis through the object or through that body. For example, say the blades of fan, they are rotating about the fixed axis in such a way, they are rotating about this axis. Or we know the example of merry-go-round. The chairs around this merry-go-round, there is a pole inside around which they are revolving. This is a type of rotational motion. So, or in such case, we say that the circular motion performed by the body is along a fixed axis, and we use the word as a rotation here. Fine. So, see, when particle is performing circular motion along the circumference, it means what happens? It displaces certain angle. As there is displacement, there must be velocity. As there is velocity, the particle should possesses acceleration and thereby nothing but the force. So, which are these displacement, velocity, acceleration and force in case of circular motion, that we will see here. See, first of all, say suppose an object lying here, it is performing, starts revolving or start performing circular motion about this. Then this is what the radius vector. What is the radius vector? Center of the circle. Say O is the center of circle. Fine. Radius vector, which we call it as position vector also, because in case of circular motion, this position vector gives the position of the particle at every instant of time during its motion. Thereby, say suppose during a small interval delta t, the particle moves from, or the object moves from this position to this position. So again, during this, it covers an arc equal to delta s, and this is what again radius vector. The angle, this angle theta, is the angle traced by the radius vector by an arc delta s. This plane angle theta, that we call it as obviously angular displacement. It is called as angular displacement. We know that this angular displacement, it is denoted by theta is equal to arc divided by radius vector. So we can define it as an angle traced or subtended at the center of circle by an arc with radius vector, that is nothing but the angular displacement. It is measured in radian. What is about this direction? Is it a vector or scalar quantity? If we consider a finite angular displacement, then it is not a vector. But if we consider for an infinitesimally small displacement theta, say suppose delta theta very small, for a very small angle delta theta, then the angular displacement is treated as a vector quantity. So its direction is along the obviously perpendicular to the plane of circle. We have seen these concepts. So this is about the angular displacement. Furthermore, then as the particle is performing like this, what is about the velocity? Then its velocity in case of circular motion, it possesses linear velocity as well as angular velocity. Fine. So what is angular velocity is, according to the definition of velocity, it is the rate of change of displacement as we have seen it in case of a translatory or linear motion. So similarly, angular displacement, it is denoted by omega is equal to, it is rate of change of angular displacement. So omega can be written as d delta theta divided by delta t. So within, suppose say we can say this theta is equal to omega times t also. Fine. So within short interval of time, say delta t, the particle moves from point A on the circumference A to B. Then what is the angular velocity with which it is moving is nothing but rate of change of angular displacement, which is delta theta by delta t. Here direction of this angular velocity is again nothing but it is perpendicular to the plane of the sense of rotation. Sense of rotation of what? Sense of rotation of the particles, which is particle which is performing circular motion along the circumference. So perpendicular to this sense of rotation, this is what the direction of angular velocity is. Fine. Now it has angular velocity as well as a linear velocity. Where does it lie? For example, say suppose particle is now at this position P, and it is released. We know about this example of, suppose say a stone tied to the string. A stone is tied to the string and reeled in a horizontal circle like this. We know about the gopher. You call it as gopher. So stone tied to the string and reeled in a horizontal circle. At a glance, say suppose the stone is released, what will happen? This stone will move tangential to the circular trajectory, and thereby we denote this is what the direction of linear velocity. It will move tangent to the circle. Thereby this is what nothing but the direction of linear velocity which will lie. Which is, say suppose the particle is at point A, it means here the direction of linear velocity is like this. It is at point B, the direction of this. During the motion, suppose it is at this point, then this will be the radius vector and the direction of linear velocity is like this, right? So if we see here, always this radius vector and the velocity vector, they are perpendicular to each other. As we have studied in 11, that is scalars and vector, we know that there is two vectors. From this we can write here as V is equal to, vector V is the vector product of omega cross vector R. Vector product of two vectors is defined as it is the product of magnitude of the two vectors and sine of the angle between them whose direction is perpendicular to the plane of sense of rotation. So here from this figure we know that the derivation about this we have studied in our 11th standard, or we can easily derive this also. So therefrom we have a relation, that is linear velocity is the vector product of, in vector notation we can write it as vector omega cross vector R, where R is the radius vector, omega is the angular velocity whose direction is perpendicular to the plane of sense of rotation or plane of the circular motion or circular trajectory. V is linear velocity. Now furthermore, when the particle has angular velocity omega, it means it possesses obviously angular acceleration, right? So what is about the angular acceleration? Angular acceleration, about which we have again studied, is nothing but denoted by vector alpha, which is the rate of change of angular velocity. Means suppose omega 0 is the initial velocity, angular velocity, omega is the final angular velocity, and within the time the change in velocity is, say suppose omega minus omega 0 divided by t. So this is what nothing but the angular acceleration alpha, or we can write it simply as delta omega divided by delta t, or limit delta by taking the limiting value of delta omega by delta theta, we can write here as delta t tends to 0, this is equal to d omega by dt. So nothing but the rate of change of angular velocity, which is nothing but the angular acceleration in case of circular motion. Fine. So these terms, theta measured in radian, angular velocity it is measured in radian per second, theta angle, it's a plane angle simply measured in radian, this is measured in radian per second, and the angular acceleration measured in radian per second square. Now again see what is about the direction of angular acceleration. The direction of angular acceleration is also along the direction of angular velocity. But see, say suppose the speed of the particle goes on increasing. If the speed of the circular motion, particle performing circular motion, it goes on increasing, then the direction of angular velocity is also in the direction of angular acceleration is in the direction of angular velocity. Or suppose if it is decreasing, like suppose the fan is switched on or switched off. Once the fan is switched on, we found that its speed goes on increasing until it will acquire a uniform speed. So before it reaching to a uniform speed, its speed goes on increasing. So during this increase in speed, we found that it possesses acceleration, and this acceleration is in the direction of angular velocity. Whereas suppose the fan is switched off, then what will happen? The speed goes on decreasing, means angular velocity goes on decreasing and ultimately it becomes 0, that is deceleration takes place. And in this case the direction of angular acceleration is opposite to that of lying along the same plane, but it is in the opposite to that of angular velocity, but along the direction of the motion. Fine. So these terms are analogous to the translatory motion, those we have studied. That is linear displacement, we can denote it by S angular velocity. Similarly, in case of a translatory motion, we know that its velocity is v, and in case of angular acceleration for the translatory motion, it is nothing but the a. So similar kinematical equations, those we can write with the help of these parameters. Say u is the initial velocity, v is final velocity of the particle during its motion, s is the displacement takes place, and it is moving with uniform acceleration. Say suppose a in time t, then we can write the three kinematical equations. Similar kinematical equations can be applied to these circular motion with the parameters, that is theta is the angular displacement, omega is the angular velocity. You can write initial as omega 0, final as omega, alpha is the angular acceleration, and t is the time within which it takes place. So similar kinematical equations of motion can be applied to the circular motion also. This is about the terms which we have studied. Now furthermore, this circular motion, it may be a uniform circular motion or it may be a non-uniform circular motion, and accordingly we can have the characteristics of this circular motion. What is about the characteristics? To study about the characteristics of circular motion, first of all we will see here what is a uniform circular motion. See, UCM. You know that uniform, that is the word suggests, it is nothing but the constant. What is uniform circular motion? Is motion of the object performing circular motion. Motion or circular motion performed by the body with what? An object performing circular motion with constant magnitude of velocity, or we can say or constant speed. Now about linear velocity we are talking about, that is an object performing circular motion with constant magnitude of a linear velocity. Where does this linear velocity lie? It is always tangential to the circular trajectory. Means, say suppose the uniform revolution of earth or rotation of the blades of fan, when it acquires or reaches the uniform speed, this is also a UCM, or motion of the tip of second hand, hour hand or minute hand. All these are nothing but the examples of a uniform circular motion. That is, it takes equal time in it traces equal angle in equal interval of time. Such a motion we call it as a periodic motion. So circular motion, it is a periodic motion. For completing one revolution it takes equal time, and thereby we call it as a periodic motion. This is what one of the characteristics of uniform circular motion or circular motion. It is nothing but it is a periodic motion. Along with, when we say that the particle is performing circular motion, the direction of linear velocity continuously changing, but the magnitude of this linear velocity, direction changes. But what is about the magnitude? Magnitude of linear velocity, if remains constant, then such type of motion is called as a uniform circular motion. See, though magnitude of velocity may remain constant or may not remain constant. If it will not remain constant, it is a non-uniform circular motion. But what is about the direction? Though it is a UCM or non-UCM, the direction of velocity continuously changing according to the change in the position of the particle. Suppose the particle is lie here, that is vector, the direction is a particle is here, the direction of velocity is like this. So likewise the direction of velocity continuously changing. So UCM is called an accelerated motion. What is about the characteristics of UCM is that it is an accelerated motion, isn't it? It is an accelerated motion. Why it is called an accelerated motion? When the acceleration is produced, whenever there is change in the velocity of the particle takes place, acceleration is produced. Velocity changes by means of either change in the magnitude or direction or both. Here the magnitude of velocity remains constant, but the direction changes continuously. Thereby there must be acceleration, and thereby we must say that uniform circular motion is an accelerated motion. This is one of the characteristics. This is about the linear velocity. What is about the angular velocity in case of uniform circular motion? Angular velocity remains constant. In case of UCM, omega is also magnitude of UCM remains constant, magnitude of angular velocity in UCM remains constant, as well as we know about the direction, that is direction of angular velocity is always perpendicular to the plane of the circle, thereby it will also remain constant. Fine. So we can again define UCM in another term as an object performing circular motion with constant angular velocity. This is also nothing but the UCM. Fine. Means in case of UCM, magnitude of linear velocity remains constant, magnitude of angular velocity remains constant. It's a periodic motion. Then what is about the non-UCM? What is about non-UCM? Obviously, it is when an object performing circular motion with changing velocity, right? Changing velocity means obviously direction of the velocity changes, direction of V always changes, but the magnitude of velocity also changes. When the magnitude of velocity changes, we must say it is nothing but a non-uniform circular motion. Fine. So in case of non-uniform circular motion, the magnitude as well as the direction of the linear velocity changes. When the direction of linear velocity changes and magnitude also changes, it means there must be change in the angular velocity also, because we have seen the relation, that is V is equal to vector omega cross vector r, and if r, obviously radius vector is constant, if there is change in the magnitude of linear velocity, there must be change in the angular velocity also. So both changes in non-uniform circular motion